One of these gemstones has sold for more per carat than many diamonds. Another was once so rare that only a handful of specimens were known to exist. Notice the color. Not pink, not brown, not purple, a deep, concentrated red. Now notice something else. The color doesn't seem to dance across the surface. It appears locked inside the crystal itself, almost as if the stone is glowing from within. To a geologist, that observation immediately raises questions. What process created such an unusual color? What happened inside the crystal? And how rare must that process be? This is a red diamond, one of the rarest gemstones ever discovered, and it is only the beginning. Red diamond, Painite, Musgravite, Jadeite, Alexandrite. Some of these gemstones have sold for astonishing prices. Others are so rare that many collectors will never see one in person. And all of them share something remarkable. Their value was determined long before they entered a jewelry collection. Their value was determined by geology. The question is not simply why these gems are expensive. The question is why nature creates them so rarely. To answer that, we need to follow the clues. The same clues geologists use when searching for them in the field. Chapter 1. The Red Diamond. At first glance, the color is the obvious clue, but geologists often focus on something else. Rarity. Not commercial rarity, geological rarity. Because creating a red diamond requires an extraordinary sequence of events. The story begins deep within the Earth's mantle, far deeper than any human has ever drilled. Carbon crystallizes under immense pressure. Ordinary diamonds can form, but a red diamond requires something more. Something unusual must happen inside the crystal itself. Tiny distortions develop within the crystal lattice. The atomic structure becomes slightly altered. Light behaves differently, and the result is one of the rarest colors in the gemstone world. For decades, most known red diamonds came from the Argyle mine in Western Australia. Yet even there, they were extraordinarily scarce. Millions of carats of diamonds were recovered. Only a tiny fraction qualified as true red diamonds. Several exceptional specimens have been valued at well over $1 million per carat. That level of rarity attracts collectors, but it also attracts geologists, because geologists want to understand why. The search begins with the host rock, kimberlite, a strange volcanic rock that acts as a natural elevator from the mantle. Most prospectors searching for diamonds are not looking for diamonds. They are looking for kimberlite. Notice the dark weathered rock. Notice the scattered indicator minerals, garnets, chromites, ilmenites. These minerals often survive weathering better than the kimberlite itself. To a trained geologist, they are clues. Clues that something deeper may be hidden below. The crystal comes last. The geological evidence comes first. That principle appears again and again throughout the search for rare gemstones. And nowhere is that more obvious than with Painite. Chapter 2. Painite. At first glance, nothing about this crystal seems extraordinary. The color is subtle. The crystal habit is unassuming. Many people would walk past it without a second look. Yet for many years, Painite was considered one of the rarest gemstones on Earth. Why? The answer begins with another clue. The host rock. Painite is commonly associated with metamorphosed marble environments in Myanmar. To most people, marble is simply decorative stone. To a geologist, marble can preserve evidence of extraordinary geological history. Notice the mineral bands. Notice the altered zones. Notice the contacts between different rock units. Those features reveal a history of heat, pressure, fluid movement, chemical change. Painite requires a highly unusual combination of elements. Nature rarely places those ingredients together. And even when it does, conditions must remain stable long enough for crystals to grow. This is why field geologists pay close attention to mineral associations. The crystal itself may remain hidden, but the environment that produced it leaves evidence. Evidence in the host rock, evidence in the alteration, evidence in the surrounding mineral assemblage. Without the correct host rock, Painite cannot form. That immediately narrows the search. And that narrowing process is how geology transforms mystery into discovery. But some gemstones are rare for an entirely different reason. Not because of unusual chemistry, because of extraordinary geological history. Musgravite. Chapter 3. Musgravite. Most viewers notice the gemstone first. A geologist notices the landscape. Before identifying musgravite, geologists often encounter the evidence that created it. Deformed metamorphic rocks, mineral banding, folded structures, recrystallized textures. These clues tell a story of immense heat and pressure acting over vast periods of time. Notice how the minerals align. Notice how layers have been stretched and folded. The rock is recording its own geological history, and that history matters because musgravite typically occurs within high-grade metamorphic terrains. The crystal is not the first clue. The landscape is. When geologists encounter these environments, they begin asking questions. Were rare elements concentrated here? Did fluid movement occur? Were conditions suitable for unusual mineral growth? Every answer leads to another clue. Every clue narrows the search. The remarkable thing about musgravite is that most people could stand directly above a deposit without recognizing it. The gemstone remains hidden. The geological evidence does not. And learning to read that evidence is one of the most important skills in mineral exploration. Yet perhaps no gemstone demonstrates the relationship between geology and value better than jadeite. Chapter 4. Jadeite. At first glance, the color captures attention. Rich green, exceptional translucency, almost glowing under the light. Collectors around the world prize this material, especially the finest variety known as imperial jadeite. In 2014, the famous Hutton Mondovani jadeite necklace sold for more than $27 million. The necklace contained exceptional imperial jadeite beads regarded as some of the finest ever discovered. The sale demonstrated something remarkable. Under the right conditions, elite jadeite can rival or exceed the value of many diamonds. But why? The answer begins with the rocks, not the gemstone. Notice the fault structures. Notice the sheared zones. Notice the serpentinite bodies exposed across the landscape. To most people, these features appear unrelated. To a geologist, they represent clues pointing toward a former subduction environment. Jadeite forms within geological settings associated with converging tectonic plates. One plate descends beneath another, pressure increases, temperatures change, fluids circulate, new minerals begin forming, and under the right conditions, jadeite becomes possible. The gemstone itself remains hidden, but the geological fingerprints are already visible. This is why prospectors search fault-controlled zones. This is why they map serpentinite bodies. This is why they study structural relationships. Because finding jadeite begins long before the gemstone appears. It begins with recognizing the environment capable of producing it. And that same principle appears once again in one of the most fascinating gemstones ever discovered, Alexandrite. Chapter 5. The gem that changes color, green, red. The gemstone has not changed. The lighting has, yet the transformation appears almost magical. Collectors often describe Alexandrite as emerald by day, ruby by night. But geologists see another mystery, not the color change, the rarity. Notice the coarse crystals. Notice the pegmatite body cutting through surrounding rock. Notice the alteration zone along the contact. Those observations immediately raise important questions. Are chromium-bearing country rocks present nearby? Is beryllium available within the system? Did hydrothermal fluids move through the contact? Without chromium, Alexandrite cannot form. Without beryllium, it cannot form either. The search therefore begins long before the crystal itself is discovered. Prospectors examine host rock relationships. They study alteration patterns. They investigate mineral associations. They trace pegmatite contacts across the landscape. Each observation provides another piece of evidence. And only when all the clues align does the possibility of Alexandrite emerge. The gemstone is the conclusion. The geology is the investigation. Red diamond, painite, musgravite, jadeite, Alexandrite. 5 gemstones, 5 geological stories, 5 examples of how nature occasionally creates something extraordinarily rare. And when rarity becomes extreme, value often follows. Not because humans decide it should, but because geology made it inevitable. Yet these gemstones are only the beginning, because during this investigation, another clue has emerged, a clue unlike anything we've examined so far. Notice the crystal. Now notice the surrounding minerals. The host rock is different. The alteration pattern is different. Even the structural setting appears different. Preliminary geological analysis suggests something remarkable. This crystal may have formed within one of the rarest geological environments known to mineralogy, an environment capable of producing gemstones so uncommon that many collectors never encounter them during their entire lives. But before that conclusion can be accepted, the evidence must be tested. The host rocks must be mapped, the mineral associations must be verified, and the geological story must be followed to its source. Chapter 6. The Blue-Green Crystal. Notice the crystal, but don't focus on the crystal first. Focus on the rock surrounding it. Experienced geologists often learn more from the host rock than from the gemstone itself. Notice the coarse mineral grains. Notice the unusually large crystals. Notice how the mineral boundaries remain clearly visible even at a distance. These are not characteristics of ordinary igneous rocks. They suggest something far more specialized, a pegmatite. Pegmatites are geological extremes. They represent the final stages of magma crystallization. As molten rock cools, common minerals crystallize first. The remaining fluid becomes increasingly enriched. Water, lithium, beryllium, boron, cesium. Rare elements begin concentrating into a shrinking volume. Eventually, conditions become ideal for growing exceptionally large crystals. Some of the largest crystals ever discovered on Earth formed within pegmatites, and many of the world's most valuable gemstones originated there. Now notice another feature. The crystal does not occur alone. Several associated minerals appear nearby. Quartz, feldspar, mica. This mineral assemblage immediately narrows the range of possibilities. Geologists call this mineral association. Certain minerals prefer forming together. When one appears, others often become more likely. The relationship provides valuable information about the environment in which the crystal formed. The crystal itself displays another important characteristic. Well-developed crystal faces, sharp terminations, minimal evidence of transport. This is significant. The crystal likely formed where it now sits. It was not carried downstream. It was not transported from another source. This appears to be primary mineralization. The crystal remains close to its birthplace, and that makes the surrounding geology especially important. Now look closer. Tiny growth zones appear inside the crystal. Different shades, different concentrations of trace elements. These internal patterns are geological records. Each zone represents changing conditions during crystal growth, slight chemical changes, slight temperature changes, slight variations in fluid composition. The crystal preserved them all. Millions of years ago, deep underground, mineral-rich fluids occupied open spaces within cooling rock. Crystal growth occurred slowly. Atoms attached layer by layer, year after year, century after century, until large gemstones eventually emerged from the process. Nature was not trying to create beauty. Beauty was simply the byproduct of geological perfection, and now a possibility begins to emerge. The color, the crystal habit, the pegmatite environment, the mineral associations. Together, they suggest a gemstone that collectors know very well. Tourmaline, but not ordinary tourmaline. Something far rarer, something geologists immediately recognize as unusual. Chapter 7. Paraiba Tourmaline. Notice the color. Unlike most gemstones, the color appears almost electric, almost artificial, yet it is completely natural. To understand why, we need to understand chemistry. Most gemstone colors come from trace elements, tiny impurities incorporated into the crystal during growth. Iron, chromium, vanadium, titanium. Each influences light differently, but Paraiba Tourmaline derives its remarkable appearance primarily from copper. That is unusual. Copper is common in many rocks. It is extremely uncommon inside gemstone-quality tourmaline. Nature must solve a difficult geological problem. Copper must be available. Tourmaline-forming conditions must be present. Both must occur simultaneously, and they must remain stable long enough for crystals to grow. That combination rarely occurs, which immediately explains part of the gemstone's value. The first Paraiba tourmalines were discovered in Brazil during the late 20th century. The discovery stunned the gemstone world. Collectors had never seen colors quite like these. Demand increased rapidly. Supply remained extremely limited. Prices responded accordingly. Exceptional Paraiba tourmalines have sold for astonishing amounts. Some specimens have exceeded the per carat value of many diamonds. Not because they are harder, not because they are older, because they are dramatically rarer. And rarity remains one of the most powerful forces in gemstone valuation. But prospectors searching for Paraiba tourmaline do not begin by searching for gemstones. They search for geological environments capable of producing them. Pegmatites, structural corridors, rare element enrichment, mineral associations. The gemstone appears only after the geological framework is understood. The investigation always comes first. Chapter 8. When rarity becomes value. At this point, a pattern begins to emerge. Red diamond required unusual crystal deformation. Painite required rare chemistry. Musgravite required extreme metamorphism. Jadeite required subduction zone conditions. Alexandrite required an improbable combination of chromium and beryllium. Paraiba tourmaline required copper-rich pegmatite systems. Different gemstones, different geological histories, yet all share the same principle. Nature rarely creates the necessary conditions, and when rarity becomes extreme, value often follows. What collectors purchase is not simply a gemstone. They purchase the outcome of millions of years of geological history, ancient tectonic activity, magmatic processes, fluid migration, metamorphism, crystal growth, erosion. Every gemstone represents the final result of an extraordinary chain of events. Break any link in that chain, the gemstone never forms. This is why geologists view gemstones differently. Collectors often see beauty. Geologists see process. Collectors see color. Geologists see chemistry. Collectors see value. Geologists see history recorded inside minerals. And perhaps that perspective makes these stones even more remarkable. If you enjoy learning how geologists identify rare minerals, interpret ancient geological environments, and uncover the processes responsible for Earth's most valuable treasures, consider subscribing. Because every rock records a story, and some of the most fascinating stories are still hidden beneath the surface. Chapter 9. The next discovery. But before this investigation ends, one final observation demands attention. Notice the outcrop, not the gemstones, the outcrop itself. A narrow mineralized band cuts across the host rock. Different texture, different weathering pattern, different mineral assemblage. At first glance, it appears unrelated, yet several unusual indicator minerals occur alongside it. Minerals rarely associated with ordinary pegmatites, and embedded within that zone is another crystal. A crystal unlike any examined so far. Its chemistry remains uncertain. Its origin remains uncertain. Even its mineral group remains uncertain. But preliminary analysis suggests something extraordinary. This may represent an environment even rarer than those responsible for the gemstones we've discussed today. An environment capable of producing minerals that exist in only a handful of locations on Earth. Before any conclusion can be reached, further investigation is required. The structures must be mapped. The mineral associations must be verified. The host rocks must be examined. And the geological history must be reconstructed from the beginning, because the next discovery may be the rarest one yet. To be continued.